Now, this video is about section 4.3 of Dummit and Foote, which is about G acting on itself by conjugation and the class equation. So in the previous video, G was acting on itself by left multiplication, and this time G is going to act on itself again, but by conjugation. And those are two different actions, so it's the same group acting on the same set, but in two different ways. And the action's different. You have to not confuse them, but also the consequences are different. So in this section, instead of having, Cayley's theorem or this business with a subgroup of prime index, we'll have the class equation, which is a really nice theorem also. And we'll be able to prove the fact about centers of P groups. So, the same group can act on the same set in different ways, and that's just how life is. So, so G will be acting on itself by conjugation. So here, if I have G and G and A and G, the action of G on A is going to be G times A times G inverse. And I'll talk about this at the end of the video, but it's actually important that G is on the left and G inverse is on the right. So let's not mess this up ever again. So a definition, just to give some vocab, we say A and B and G are conjugate in G if there exists little g in G with G times A times G inverse is equal to B. Now, it might look like a lot of in G, right? There's like A and B are in G, they're conjugate in G if there's G and G, and it's kind of like, why do you keep saying that? But it's because I could say, in a different world, I could say A and B in G are conjugate in H if there exists H in H with H A H inverse is equal to B, right? So it's important to specify when you're saying that two things are conjugates where there are conjugates. Oh, actually, conjugate is the verb and conjugate is the noun. So I should have said A and B are conjugates. Okay. So I think you have to say are conjugates in G if there's G and G with GA, G inverse is B. Okay, sorry, I do not mean to teach you bad English. English is not my first language, so sometimes emphasizing like this is difficult. But hopefully, you're not getting bad habits from me. Okay, but going back to the matter at hand, right, this business of like, where are you conjugates in G and H or whatever, right, is something that comes up in the homework this week, homework 5, where there's like two elements of a CeLO P subgroup, and they're conjugates in G if and only if they're conjugates in the normalizer of the CeLO P subgroup. So, we're playing here on like this part, right? Where does the element belong that makes the conjugation? Like, can we make sure that this element is actually in a smaller subgroup, or does it have to be like in the bigger subgroup? Anywho, so this is the same, right? So this definition, this is the same as saying that A and B belong to the same orbit of the action of G on itself by conjugation. All right. So just like in the previous video, I'm going to give a generalization of this now. So in the previous video, when G was acting on itself on the left, the generalization was that G could act on the left cosets of a subgroup on the left. Here, the generalization is to subsets. So I'm going to let S be a subset of G. Okay, and note, like, this is not pointy. This is a subset, not a subgroup. And we can say that G acts on S by forming the set G as G inverse, which is just the set of all elements G as G inverse for S in big S, right? So it's like we've conjugated subgroups a bunch, but we could have just conjugated subsets, right? It didn't need to be a group. It just had to be a set. And so we can do that. This gives an action of G on the power set of G, which is just defined to be all subsets of G. Right? So in particular, right, what I'm saying is that this here, when I take a subset S and I conjugate it, this is just another subset of G. Okay, and so now we can have the definition, and this time I will not mess it up. Two subsets S and T and G are conjugates in G if there exists G in G with G as G inverse is equal to T. So again, this is the same orbit under the conjugation of G. So a nice theorem, which actually follows from a general theorem on group actions. So this is something I've said before. One thing that's nice is that you can study general group actions, and then by specializing the theorem to the specific group action, you get, special theorems. So here we have proposition 6 from the group, from the book. So if S is a subset of G, the number of conjugates of S is equal to the index in G of the normalizer in G of S. Okay, which this is just defined to be G in G such that G as G inverse is equal to S. Maybe it happens, right, that something fixes S by conjugation, and then you put it in a normalizer, and the index of this normalizer is the number of conjugates of S. And let me just say the other, well, no, let me, let's call this maybe proposition 6.1. And the proof is that the number of conjugates, this is the size of the orbit containing S, and this is the index of the stabilizer of S under this action. And so we had a theorem that said that the size of the orbit was equal to the index of the stabilizer in G. And here, when you just rephrase it in terms of this conjugation action on the set, it just says this. So it's not really a new theorem. Now, I do not want to write in blue, so let's write in black. So the second part of the proposition, so this is together in the book, is that if little s is an element of G, the number of conjugates of this little s is equal to the index in G of the centralizer of S in G. So now this is the same theorem. I know it looks different because here I have a centralizer instead, but that's because, right, so the proof is simply that the normalizer in G of a set with one element is the centralizer in G of that element. And that's because, right, to normalize a set, right, so if G, this set, G inverse, is equal to this set, it means that G as G inverse is equal to S, because it can't go anywhere else, right? Here there's a difference between the normalizer and the centralizer, because all I want is that this set be this set, right? I'm not saying that each element like fixes the set point-wise, like that, little S1 in here goes to little S1 and little S2 goes to little S2. They can get jumbled. So it's not the centralizer. But when I'm talking about a set with only one element, then there's nowhere to jumble to. There's no difference between normalizing and centralizing, because you can't say, oh, well, maybe conjugation sends little S1 to little S2. There's only one S. So again, this is the same theorem. All right. So now I want to talk about this a little bit, this number of conjugates, and make a remark that notice that G is alone in its conjugacy class. Oh, I forgot to define that when I defined. So conjugacy class is just the set of conjugates of an element. Right? So we remember that the orbits of a group action form equivalence classes in the set on which G is acting. So when the specific action is conjugation, the equivalence classes are called conjugacy classes. Or the conjugacy class or the equivalence classes of the conjugation action. So anyway, G is alone in its conjugacy class if and only if G belongs to the center of the group. Why is that? Well, the size of the conjugacy class is 1 if and only if, right, H inverse is equal to G for all H in G, and that's exactly what it means to be in the center of the group, right? Conjugation never sends you anywhere else than yourself, which means that you commute with everyone. So with this said, we are ready with the class equation. We are ready for the class equation. It's such a good theorem. I don't want to cram it at the bottom of a page. These are not real pages. No trees are being harmed, so I'm just going to treat myself. So the class, which is theorem 7 in the book. Okay, so I'm going to go ahead and let G be a finite group. And I'm going to say that G has R conjugacy classes outside of its center, right? Like, just the idea is that, you have your whole group G. Here you have the center. Everybody is its own conjugacy class. Like, you just have one conjugacy class, another conjugacy class, another conjugacy class, another one, right? Like, the center is just like everyone from themselves. And then, like, outside of the center, you have like one conjugacy class, another conjugacy class, another conjugacy class with like different elements in there, right? So this one like contains different elements. Okay, so in this picture, there's 4 conjugacy classes outside of the center. Okay. Let G1, G2, up to GR be representatives for these classes. Okay, so I just go here, right, and I'm like, okay, you are going to represent your whole conjugacy class, and you are going to represent your whole conjugacy class, and you are going to represent this conjugacy class, and you are going to represent this conjugacy class. You just pick one element from each conjugacy class. Then the size of G is equal to the size of its center plus the sum of I from 1 to R of the index of the centralizer of GI in G. And the proof is basically this picture, right? The size of G is how many elements are in here. How many elements are there? Well, there's this many that are in the center. These are all their own conjugacy classes, so whatever. And then, right, you count by conjugacy class, right? How many are in this one? 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 But we just said how many are in each of them is the index of the centralizer of an element in the group. So that's all that this is saying. It's just repackaging this fact here and going over all of the elements of the group and saying, well, everybody belongs somewhere. Okay, so the class equation, when I prove it like this, I make it look so easy, but it actually has as a corollary some really nice facts. So theorem 8 is let P be a P group. So we talked about it in class on Monday. This means that the size of P is P to the A for P prime. Okay, so the size of P is a power of P. Then the center of P is not just 1, right? So 1 always commutes with everybody, but in a P group, there's always other elements that commute with everybody. And the proof is P divides the order of G, duh, and P divides the index of the centralizer of G in the index of the centralizer of little gi in the big G, right? So I'm just using this notation here, and because that's not 1 if gi is not in the center of the group. Okay, so now looking at this equation, P divides this term, P divides each of these terms, and therefore this, and therefore P divides the size of the center, so the size of the center cannot be 1. It has to be strictly bigger than 1. It has to be strictly bigger than 1, and so it's not trivial. So you see the class equation, right? This action by conjugation is actually really nice and gives you this theorem. And it will give us a corollary, so corollary 9. So if the size of P is P squared, again for P prime, then P is abelian. And once we've proved the classification theorem for abelian groups, we'll see that, in fact, P is isomorphic either to the cyclic group with P squared elements, or P is isomorphic to the cross product, direct product of 2 copies of the cyclic group with P elements. These are the only 2 abelian groups with P squared elements, and actually they're the only 2 groups with P squared elements. Okay, so if you're keeping track, like if the size of P is just little p, then P is the cyclic group with P elements, and if the size of P is P squared, then P can be either the cyclic group with P squared elements or cross product of these 2. So primes are nice, not much can happen with them. And this proof is also nice. so I will give it. I only give proofs that are nice. I only give proofs that I think you should know. Like, you should be able to reproduce these given a little bit of time, like a qualifying exam amount of time. There's definitely theorems that are, hard to prove and like require difficult ideas, but there's also things that you should be able to just do. Okay, well, the proof is that since P is a P group, the center of P is not 1. So in particular, the center has size P or P squared, right? Because the center is a subgroup, and therefore its order has to divide P squared, and the only other numbers that divide P squared are P and P squared. So then the size, right, the center is normal, so P mod ZP is a group. It has order 1 or P. So in either way, P mod ZP is cyclic. I mean, really, right, if we have this, we get automatically that P is abelian, because the center of a group is abelian, so P is its whole center, so it's abelian, but, whatever. Okay, so if P mod ZP has order P, then it's cyclic, and we showed this implies that P is abelian. This is homework 3, problem 4b. Whenever any group mod its center is cyclic, not necessarily of prime order, any cyclic, then the group has to be abelian. So hopefully you did do this proof. If you didn't, if you couldn't do it at the time, make sure that you do it, or that you ask me how to do it. That's an important proof to know. Okay. This section has a ton of stuff. There's a few words about conjugacy and SN, which I think is important to know, might come in handy, you never know. So conjugacy in SN. So so the symmetric group, right? So I'm gonna let tau and sigma be in the symmetric group on n elements. Then if I conjugate sigma by tau, okay, like in words, this element is just sigma, but in it replace I by tau of I. Okay, so maybe this is weird, so I'll just do like a really simple example. So say I take tau to be 1, 2, so in particular tau inverse is also 1, 2, and I take sigma to be the cycle 1, 2, 3, then tau, sigma, tau inverse, or, 1, 2 times 1, 2, 3 times 1, 2, well, that's just sigma, okay, so it's going to be like a 3 cycle. But in it, I replace each number by where it goes in tau. So 1, I look in tau, it goes to 2, so I'm going to replace 1 by 2. And 2, I look in tau, tau goes to 1, so 2 goes to 1, so I'm going to replace it with 1. And 3, I look in tau, 3 doesn't go anywhere, so I'm going to leave 3 alone. And you can check this multiplication to see that it is true. And so you see that the shape of sigma doesn't change when it's being conjugated. Like sigma was a 3 cycle, it's still a 3 cycle. And I want to make this more precise. So definition, if sigma is the product of R disjoint cycles, and like this is unique, right? The decomposition into disjoint cycles is unique for elements of SN. So like sigma is the product of each disjoint cycle of lengths. Ooh, I don't know what. I mean, I know what happened, but I don't want to talk about it. Of lengths n1 less than or equal to n2 less than or equal to n3 less than or equal to less than or equal to and R. Okay, so what do I do? Okay, what's going on, right? I have sigma is a product of R disjoint cycles. Disjoint cycles commute. So I just look at the cycles and I order them from like shortest to longest cycle. Or like if there's two cycles, I put them next to each other in whatever order I want, right? But I just do like little cycles and bigger cycles and the biggest cycle. Okay, and I just like record their length, like lengths 2, 2, 3, 4, 5, 5, whatever. Okay, that would be like a huge permutation, but that happens. Okay, then the cycle type of sigma is N1, N2, N3, up to NR. Okay, and that's what I referred to like as the shape before. Like here, like sigma was just a 3 cycle, or sigma could be a 2 cycle times a 3 cycle. They're disjoint, right? Or it could be a 2 cycle times a 3 cycle times a 4 cycle. That's its cycle type. It's just the shape of it. I'm not even telling you the numbers in it. I'm just telling you the lengths of the cycles. Then proposition 11 in the book says that 2 elements of Sn are conjugates if and only if they have the same cycle type. Okay, that's because, as we see here, right, conjugation preserves the cycle type. So, certainly, if 2 elements are conjugates, then they have the same cycle type, because when you conjugated, you didn't change the cycle type, you just changed what numbers went into each position. But the other direction, right, this is an if and only if, this is just to say that if I have any 3 cycle, I can make it be conjugate to this by taking the correct permutation, right? So say, if I want to exhibit like, is, 1, 2, 3 conjugate to 3, 4, 5, yes, right? Yes, use tau is equal to, okay, so what do I want, right? I just want tau to send 1 to 3, so I'm going to say that. And then I'm going to need 3 to go to 5, so 3 is going to go to 5. And then 5 can go anywhere I want because there's no 5 here, so it won't affect anything. So I'm just going to close this cycle. And then I need 2 to go to 4, so I'm just going to do that. 2 goes to 4, and then there's no 4 here, so I don't care where 4 goes, so I'm just going to close that. And then I need, 3 to go to 5, but 3 goes to 5, I already took care of that. And so this is true. If I make this be sigma, then this should be tau sigma tau inverse. Hopefully you can check this at home, and I did it right. I just did this on the fly, actually. Okay. The book has a little bit about centralizers in SN using, right, because there's this class equation with the sizes of centralizers, but I don't want to talk about that because this video is getting super long already and it's not super interesting. And so I will just bring up a remark that I think is really interesting that comes up in this section about showing that A5 is simple. So this is like kind of apropos of nothing the way I'm going to do it, but actually in the book it comes up as showing that A5 is simple. Okay, but note that H is normal in G if and only if for every conjugacy class C, either the whole conjugacy class is in H or the conjugacy class in H don't intersect. And that should make sense because for H to be normal in G, right, it means that G inverse is equal to H for all G in G. And so it means that like every little element of H, if it's in H, every one of its conjugates is also an H. So that's exactly what I'm saying. If I have a conjugacy class, either it has nothing to do with H and then whatever, or the whole conjugacy class is an H. And so this is why you can show that, this is how you can show that A5 is simple, because if A5 had a normal subgroup, then it would contain like a full conjugacy class. This subgroup would contain a full conjugacy class, and then you show that that's not possible. Okay. Another kind of unrelated, but of course related topic is right versus left actions. And I don't want to say too much about this, but I thought that this was super cool because I had never thought of it that way. So just considering conjugation, if I do G inverse and I call it the action of G on A, this is a left action. I've been doing this, this whole video and a little bit before, so you would hope that would be true. But if I do G inverse AG and I call that the action of G on A, then this is a right action. What? Okay. And I just want to note, right, I could say that this is the action of G inverse on A, and that would be a left action. And I could say that this is the action of G inverse on A, and that would be a right action, right? So it's just like, if I want to say that this expression is how G acts on A, then this has to be a left action. And if I want to say that this expression instead is how G acts on A, right? So I'm just like, oh, how does G conjugate A? If I think that G conjugates A like this, I'm talking about a left action. If I say that G conjugates A like this, then I'm talking about a right action. And why is that, right? Well, it's because of how it has to work when you compose your actions. So if you have GH acting on A on the left, right, with the action that I gave before, right, that's GH A GH inverse, and that's GH A H inverse G inverse, you see that this is GH A H inverse G inverse, so this is H acting first and then G. So it has to be a left action so that H acts first and then G acts on that. Whereas if I do the other action, so this one was GH inverse A GH, like that, if I expand it out, I get H inverse G inverse A GH inverse. I see that this is H inverse G inverse A G H, and now it's G that acts first, right? So if I do inverse element, then the element that's on the left will act first, and therefore this must be a right action so that G is touching A first. Whereas if I do element inverse, then it's the element that's on the right that acts first, so it has to be a left action for it to make sense. I hope that this makes sense to you because I thought that it was really cool to think about. And it's actually really, really common to write conjugation this way, right? To write conjugation this way. And those people are just thinking of conjugation as a right action. And that's fine. Conjugation can be a right or a left action depending on how you set things up. This book sets up conjugation in this manner as a left action. But don't be surprised if you read in other books this conjugation. And this one is often noted like this, like kind of exponentiation. And we always reserve this notation for the right action for this one, right? So the little g is on the right of A, and it's for us to keep our sanity. We would not write this for that. And the last thing I want to say about left and right actions, I kind of actually like gestured at here, is that if GA is a left action. Then G inverse I want to say this correctly. Then I can get a right action by having G inverse act on A under this action. So I have two actions here, right? Maybe I have like this is like a new like red action, like a new red right action, right? So this different action is just like this old action, but by G inverse is a right action. And vice versa. If I have a right action, then I can get a left action by doing my right action, but by the inverse. And so every left action gives rise to a right action, and every right action gives rise to a left action. They're corresponding actions. But it's important to keep track of them and be comfortable with both because they both arise naturally. But also at the same time, they're not that different. So you shouldn't let that confuse you too much. All right, I think that's enough for this video.